Alright, so here we are with the 6-1 notes for geometry. We are going to specifically be going into four-sided shapes soon, but our first lesson here on Chapter 6 will be about all polygons, meaning all two-dimensional shapes. We're going to name them via their sides and their angles, and then we're also going to use measures of the interior of a polygon as well as the exterior. So taking a look at your properties and attributes of polygons, the side of a polygon, of course, is formed by connecting two vertices. So we have a side here mentioned as AE. We also have AB, BC, CD, and DE. So all of those 5 sides make up that polygon. Then you have a vertex, and again, the vertex is connected to make a side. And so vertex A and E, for instance, makes side AE. And of course, plural is vertice. And then your diagonal, that's mentioned here. It's a segment, and this will be used quite a bit here. A segment that connects any two non-consecutive vertices. So if we think of kind of this alphabetical order of going around this 5-sided shape, if I have A to B, that's consecutive. They're right after each other in the alphabet, right? B to C, C to D, D to E, etc. And so if I want to connect two non-consecutive vertices, that would be like A to C, because in the alphabet they're not next to each other. A to D, they're not connected to each other. However, A to E in the alphabet are not connected, but in this diagram they are, so that's kind of where the trick comes in the relationship of that story. But anyway, so those are your diagonals, vertices, and sides, just so that we have those key ideas. Taking a look, and you probably know a few of these. These are number of sides of a polygon and then their name. So of course a 3-sided polygon is a triangle. We've been doing a lot with those. This unit is going to be a lot of 4-sided polygons, which is going to be your quadrilaterals. A lot of you might think rectangle or square, but those are specific quadrilaterals, and quadrilateral is the entire family of 4-sided shapes. Then we've got our pentagon, so that's your 5-sided shape. Hexagon, you've probably heard. Probably not heptagon. That's your 7-sided shape, so that's probably one that you're going to need to at least have reference to this chart or kind of remember exists. We also have octagon. You've probably heard of that one. Probably not a nonagon. That one is probably new to you as well, but non meaning 9 sides. Decagon, decade, decimal, has that 10 in it, and so that's your decagon. And then we also have dodecagon, which is 12. I just think that one's kind of cool. Basically, after 10, though, we just start using something called Ngon. So if you have a 36-sided shape, you're just going to say it's a 36gon. We don't have a nice prefix for that. So, all right. So those are your names. And so within some of these problems, they will tell you what the shape is based on the name versus the number of sides. So you just want to be able to convert between the two. All right, so taking a look at these, we're going to tell whether the figure is a polygon. If it is, we're going to name it. Turns out polygons have to have nice straight sides. So sorry, you are not a polygon, all right, because it's got this curved side. This, again, curved side can't be a polygon. And this one is not even complete, so it's not even a shape. It's potentially a curvy line, so no. So those are not polygons, and the rest of them are. Even though this one is in the shape of an arrow, you might think, well, that's just a picture. But it does technically have just all straight sides connected, and so it's a polygon. It's just not what we think of as a regular polygon, kind of like this one here, or even this one. So we're going to go ahead and count the number of sides so that we can label them, or give it its name. So we've got 1, 2, 3, 4, 5, 6 sided, and so that's going to be a hexagon. This one we've got 1, 2, 3, 4, 5, 6, 7 sides, so that one's going to be your heptagon. And then our last one here, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's your nonagon. All right. So again, nice straight sides that are all connected. That's a polynomial. Or sorry, polygon. All right. So we also have, and I mentioned it just recently, regular polygons. That means that it is both equilateral, meaning same length sides, as well as same angle measures. So we tend to see a lot of regular polygons within, signs and things like that. But, of course, life is more of irregular, okay? So these are your regular polygons versus taking a look at the previous one. This, for instance, is your irregular polygon, but still a polygon. So all right. Another piece that we're going to talk about here is concave. So concave, again, is usually what we don't see when it comes to polygons in our head, I guess. Concave means that it's going inward, okay? And so if we kind of think of this one here, for instance, going inward and then out, that is going to mean that it is concave. Versus convex is kind of like if you, like a balloon, like you're going to blow it out versus it kind of caves in. And so that's your convex. Okay, and perhaps you've been in science when we talked about convex and concave lenses and things like that. So it is that same concept. There's either bowing out or kind of bowing in. The official definition of concave, however, is actually very interesting. One of the vertexes is located inside of a diagonal. So if we connect, for instance, on this arrow, one vertex not to the next vertex, but to the non-consecutive vertex, it turns out that instead of being outside, this vertex is inside, and that's what makes it concave. And so that's what they're kind of showing here. This point is within the diagonal versus outside of the diagonal. If I drew this shape so that it was outside, it would be convex. It would be outward versus concave of inward. So it's an interesting way to think about that, especially since we were just going over that idea of diagonals. Alright, so this next one here, we're going to identify if this shape is regular, meaning all of the sides and angles are the same, and at that point, if it's concave or convex. So first I'll go through and identify if things are regular or irregular. So the best way to note that is if each of the sides is being mentioned as the same. So notice that every side has one tick mark, but not every angle has one tick mark. You have a 1 tick mark angle and a 2 tick mark angle. So this one is irregular. Same thing as this one, these sides are clearly going to be bigger than this side, and so that's not necessarily going to happen as being the same length, so this one is also irregular. Next one, we've got all tick marks here, and all of the angles have 1 tick mark, and so that one is our first regular example. Over here, this sideways square is also regular, all the sides are the same and all the angles are the same. And then this last one, sadly, is irregular, because as much as you might think the angles are the same, they didn't mention what this angle measure is, so we can't necessarily say that that happened. And then the next piece is concave or convex. So again, if you can connect a diagonal, for instance, and the point is on the outside of that diagonal, then you have a convex. So this is convex. This one's concave. Again, because I could connect these two and notice that it's inside the shape versus outside, so it's concave. This one's convex as well, convex. And then our irregular one is concave. Again, kind of looking at the example from the previous page, we've got this inner piece, so that's concave. All right, then we go to this idea of interior angle measures. So, for instance, we know that in a triangle, there are 180 degrees, right? Okay, and so that's kind of what this is mentioning here. But because there are triangles within all of these polygon shapes, you then get to add up a bunch of 180 degrees because of the numbers of triangles. So, basically, if you draw all of the diagonals from a single vertex, okay, so that's, it's easier to see from here. Single vertex drew all of the diagonals possible. The number of triangles that you have means that that's how many 180s is inside of it, or how many 180 degrees. So this quadrilateral, for instance, has two 180-degree triangles in it, and so therefore all of the angles added up together are going to have to add to 360 in every four-sided shape. Same thing happens here with a pentagon, only now if you draw those diagonal triangles from one vertex, you actually have three 180s, and so that means that you are going to have 540 degrees total in a pentagon. The next one, your hexagon, add another 180 to that, and you have 720 degrees that are going to be total inside of every single hexagon. Every single convex hexagon. Alright. So, this pattern that we've just talked about, we've got one triangle inside, two triangles inside, three triangles inside, etc., actually ends up making a formula, of course. So, triangles, as we know, have three sides. There's one triangle within a triangle, and so technically there are 180 degrees inside of that triangle. Quadrilateral has four sides, has two triangles inside of it, and therefore has 360 degrees. So it turns out if you continue this pattern, we realize that if you take this side length, or number of sides, subtract 2, you get the number that you're going to multiply by 180 in order to get your number of degrees. So this formula is very key. You can see that it's down here in our polygon angle sum theorem. If you have the number of sides, which is n, of any shape, in order to make that shape, or if you're kind of evaluating it, you would take that number of sides minus 2 times 180, and that will tell you the interior angles. That are necessary inside of it. So for instance, if you have a 36-sided shape, take away 2, you get 34 that you're going to multiply by 180. And so a 36-sided shape actually has 6,120 degrees inside of it. So it's very large. Lots of obtuse angles on that one. Alright, so let's apply this. We're going to find the sum of the interior angle measures of a convex heptagon. So a lot happening here. First thing is that we know that the sum of the angles is going to be n minus 2 times 180. And then we're given heptagon, and so we know that n is 7. So if we plug that in, the number of interior angles, or the measure of all of the interior angles, is going to be 7 minus 2 times 180, or 5 times 180, or 900. So there are 900 total degrees inside of a heptagon. Alright, so let's see then, we want to find the measure of each interior angle of a regular 16gon. Okay, well, to get all of the angles inside of that 16gon, we're going to use our n minus 2 times 180. Notice that our n is 16, so we'll plug that in. So we get 14 times 180. Oops. Alright, and so that's how many are in total. But of course, notice that it actually asked each interior angle. So we want the measure of each interior angle. And so since it's a 16-sided shape, we would divide by 16. 16 sides means 16 angles. And so each angle has that number divided by 16, which is 157.5 degrees. So again, this first number here might feel like it's the answer, but since they want each interior angle and not, as we noticed in here, the sum of the interior angles, each one means we'll have to divide by 16 versus put them all together. Alright, so how might this work? Well, in this next one here, we have an image of a 5-sided shape, so a pentagon. It says it in there. And so we're going to find the measure of each of them. Well, in a pentagon, as we saw in our graph here, or sorry, table, it's 540 degrees. So pentagon has 540 degrees, but notice that each of these degree measures is given as some sort of multiple of c. So if I want to find out what c is, or each measure of each of these sides, every single angle that I have is going to add to be 540 degrees. So angle C plus angle D plus angle B plus angle A plus angle E, all of those are going to have to add up to be 540 degrees, otherwise it's not a pentagon, it might be convex or something. So if we add each of these together, that means that we'll have a certain number of C's. And so we have 135 C's, which makes 540. But, of course, let's divide to find out what each of the C's are worth. So 540 makes 4. And so in that case, our C is 4. Now it does say find the measure of each interior angle, so that means that I need to put a 4 in for all of these C's that I see in this diagram. So angle C is going to be 32 times 4, which is 128 degrees. Angle D is the same composition, so 128 degrees. Angle B is 18 times that 4, so 72 degrees. E is also 72 degrees. And then A is 35 times that 4, so 140 degrees. So each of the angle measures is listed up there. All right, the last piece is exterior angles. So what we've been doing inside previously was interior. Notice all the values inside of the angle. And so now we're doing exterior, so outside. Interesting part about outside angles is that all of them are 360 degrees. So it does not matter what shape we have. Here we have a triangle, and here we have a pentagon. Doesn't matter which one we have, every single one of them, if you make the exterior angles, will make 360 degrees. So the only piece about this that's probably new is making an exterior angle. So right here I'm tracing the actual triangle itself, but to make an exterior angle, it's not this entire outside loop. It's extending one of the sides of the triangle and talking about that adjacent angle. Extending the next side and talking about its adjacent, and then that final side and its adjacent. So it's always those outer angles, but not necessarily the entire outer angle. We're not talking about all of this with the 180. Alright, so on that note, this next one here, we want to find the measure of each exterior angle of a regular 20gon. Well, we know that exterior angles, no matter what it is 360 degrees, but they're telling us we want each of them. So that means that I need to take the 360, divide by the fact that there are 20 sides, and now I know that, what is it, 18? 360 divided by 20? That there are 18 degrees on every exterior angle. So if I wanted to construct a 20-sided shape, I would know that each exterior angle that I formed would have to be 18 degrees, which means that the interior angle is very obtuse. Alright, and so the last one here is just kind of putting this all together. It's saying, hey, now that you got one of them, let's go ahead and see that all of these are exterior angles of this hexagon. And so we need to find out what B is. It doesn't want to get all of the angle measures, so we don't have to plug it back in. But we do want to take all of those and realize that every single exterior angle added together is going to add to be 360. So we have 33 B's and 16 B's, 10 B's, 28 B's, 15 B's, and 18 B's, and all of those added together are supposed to make 360 degrees. 1, 2, 3, 4, 5, 6, yeah. Alright, so I'm going to add each of those numbers together to find out how many B's we actually have. And so altogether there are 120 b's. And so to get b by itself, we divide by 120 and get 3 as the b. And again, most of the time they'd have you plug that back in, but b is actually the value of 3. So, key things about this unit, you got to make sure that you got to see if they're talking about exterior or interior angles, okay, because there's going to be a different formula versus just knowing it's 360. We also need to understand if something is concave or convex, so kind of that idea of puffed out or caved in. Regular we talked about as having the same side shapes as well as, same side lengths, as well as polygon names. You need to know if you hear decagon that means 10 sides as well. So that's properties and attributes of polygons, and again we will be moving on more to quadrilaterals after this, but we just need to know all polygons have certain things going on before we can specifically go to those.